Imagine trying to point a laser at a single coin. Now imagine that coin is hundreds of miles away, and you're moving at over 17,000 miles per hour. Sounds impossible, right? Well, that's pretty much the challenge satellite engineers deal with every single day. And getting that pointing accuracy perfect is absolutely critical for, well, for everything from snapping photos of distant galaxies to beaming the internet down to your home. Today, we're going to break down a really fascinating new scientific paper that just might have cracked the code for achieving true pinpoint satellite control. So here's our roadmap. First, we'll get a handle on the pointing problem itself. Then, we'll look at a clever way controllers try to predict the future. We'll find out what was missing from the old methods, and then we'll introduce the star of the show, this new controller, the LB-FOMPC. And then comes the fun part. We're going to put it to the test, see the results, and wrap up with why all of this really matters for the future of space. All right, let's start with the core challenge. We're talking about hitting an unbelievably small target from a massive distance, all while you're zipping through the vacuum of space.
Think about it this way. You know when you try to take a long exposure photo of the stars at night? You need that camera to be perfectly, absolutely rock solid, otherwise the whole thing just turns into a blurry mess. Now imagine trying to do that, but your camera is mounted on a platform that's constantly moving. That, in a nutshell, is the problem we're trying to solve.
The technical name for this whole game is attitude control. It's all about managing the satellite's orientation, its roll, its pitch, its yaw. But forget the jargon. In simple terms, it's the art of pointing the satellite exactly where you want it, and more importantly, keeping it pointed there.
So how do they do it? There aren't little rockets firing all the time. The secret sauce is something called reaction wheels. Picture a figure skater spinning on ice. When she pulls her arms in, she spins faster, right? It's all about the conservation of angular momentum. Reaction wheels use that exact same principle. To turn the satellite left, you spin a heavy wheel inside it to the right. The satellite's body has to react, and it turns left. It's an elegant dance of physics that allows for incredibly fine adjustments.
Okay, so you have the wheels, but controlling those wheels needs a very, very smart brain. And that's where a technique called model predictive control, or MPC, enters the picture. It's a much more intelligent way to give commands.
So a simple controller is purely reactive. It just sees an error and says, oops, I'm off, let me fix it. But MPC is on another level. It's like a chess grandmaster. It doesn't just think about the move it's making right now, it predicts several moves ahead. It calculates the absolute best command to give right now to make sure the satellite will be perfectly on target a few moments into the future. It's proactive, not reactive.
But here's the catch. Even with these super smart predictive controllers, there was a problem. A couple of really crucial pieces of the puzzle were missing, and that created a serious risk for any real-world space mission. So it really boiled down to two major gaps in the research. First, stability. Scientists had come up with an even more advanced version of NPC, but there was no mathematical proof that it was actually stable. Could it, under just the right conditions, go haywire and spin out of control? Nobody knew for sure. And second, feasibility. There was no guarantee that the commands the controller came up with were physically possible for the reaction wheels to perform. That's a huge problem. You can't have your controller telling the satellite to do something it can't actually do.
And this, right here, is where the breakthrough happens. Researchers developed a brand new controller designed specifically to solve these two problems. It's called Lyapunov-Based Fractional-Order Model Predictive Control, or let's just call it LB-FOMPC.
This new method is a first of its kind. It adds two secret ingredients. The fractional order bit gives the controller something like a memory. It lets it learn from the entire history of its past movements, not just the last one, which allows for much smoother control. And the Lyapunov-based part? Well, that's the real game changer. It's a complex mathematical framework that acts like a safety net, providing a hardcore formal proof that the system will always be stable and its commands will always be physically possible. So you've got this new controller that's guaranteed to be stable and feasible. What do you do next? Well, you throw it in the ring and see how it does. The researchers put it head-to-head against the previous best-in-class controller in a detailed simulation. The theory all sounds great, right? But what about the real-world performance? How much of a difference did this new approach actually make when the rubber met the road? The results are, and I'm not exaggerating here, staggering. The new controller slashed the mean absolute pointing error by 53%. That's more than doubling the accuracy of the old method. Just an absolutely massive leap forward in precision.
And it's not just more accurate, it's way faster. The time it took to lock onto a target was literally cut in half. It dropped from about 3 seconds down to just 1.5. It's twice as nimble.
And this table from the paper just drives the point home. This wasn't a fluke. I mean, just look at the numbers. It doesn't matter how you measure the error, MAE, RMSE, you name it, the new controller is significantly better across the board. The improvements are huge, and they're consistent. And this chart just makes that speed difference crystal clear. It shows how long it took for the satellite's roll to stabilize. The old controller took 3.2 seconds. The new one, just 1.8. It's a perfect visual of that massive speed up we were just talking about. Okay, fine. It works great in a perfect simulation. But space isn't smooth. You've got things like solar wind and tiny gravity shifts that can push a satellite around. So the researchers added these disturbances into the simulation. They wanted to know, how does it handle a bumpy ride?
And this is where things get really, really interesting. Look at this. Under pressure, the old controller's performance just falls apart. Its error skyrockets, but check out that bottom row. For settling time, it just fails to settle. It can't cope. The new controller, on the other hand, stays tough. Sure, it takes a little longer to lock on, but it handles the disturbance and it gets the job done.
So the crucial point here, the big takeaway, is that the new controller isn't just better under ideal conditions, it is far more resilient, far more reliable when things get messy, which in space they always do.
Which brings us to the big question, right? A 53% reduction in error is fantastic for the scientists, but what does it actually mean for the rest of us back here on Earth?
Well, the impact is actually huge. For science, it means space telescopes can hold steadier, giving us images of the universe that are sharper than ever before. For communications, it means satellites can lock onto ground stations faster and more reliably. Think better weather data or more stable satellite internet. And big picture, it just means our missions are more efficient and our satellites are way more robust, better prepared to handle the harsh realities of space.
You see, this kind of breakthrough doesn't just improve what we're already doing in space, it opens the door to things that maybe weren't even possible before. It really makes you wonder, with this kind of near-perfect stability now on the table, what else could we achieve out there?